Hello and welcome to our Unit 2.5 Part 2 of our notes. It's for periodic trends. So it's at our learning target. I can understand and explain useful ways to compare and organize the elements on the periodic table. So last class we color-coded the periodic table and noticed that certain types of elements were bunched together. Okay, now we're going to focus on the element properties, like their size and how they relate to other things. So, okay, here we go. So the first thing we're going to talk about is atomic radius. Now, this was a vocab word. So we're going to talk about what are the trends among the elements for the atomic size looking at the periodic table. Now, this was a vocab word, but basically it's from the middle of an atom to its outer edge. So it's basically what's happening to the size of an atom, basically, as you move across the periodic table. All right, so in general, so atomic size or atomic radius, the size increases from top to bottom within a group, okay? So as you move down a group from top to bottom, the size gets bigger. The radius gets longer. And this is because the outermost orbital size increases as you move down a group, making the atom larger. So if you think about our Bohr model, so every time we move down to a new period, we add an energy level. So that's basically why they get bigger. Now here's a strange part. As you move from left to right across the period, you're actually getting smaller. So as I move from, like, let's say, potassium across all the way to bromine, potassium is going to be a lot bigger than bromine. And this is because there's an increased positive pull from the nucleus, bringing the electrons closer to it. So my analogy here is, so if I'm standing in the center and my child or whatever is like in the second row, and I want them to get even closer to me, I would pull them in. So as I move across the periodic table, they're actually getting smaller because the nucleus is pulling those electrons closer to it. All right, and if you wanted to put numbers to it, you could, but you don't have to. It's just to show you, so like here's the potassium in the period 4. Notice how it gets smaller and smaller and smaller and smaller. So bromine is a lot smaller. You won't have to know these numbers or anything. It's just the picometers on how we actually measure the radius, okay? And then if you look here, let's say in group 1, as you move down a group, they get a lot bigger, okay? So just notice the size of the circle, it's getting bigger because you're adding those energy levels. On your notes, you need to label this picture with your arrows. So generally decreases as you move from left to right, meaning you get smaller. And then generally increases from top to bottom as you go down. And generally just means there's a couple elements that like to kind of not follow the rules, but for the most part, this is the trend. All right, the next thing we're going to talk about is ionic radius. Now we haven't, the base word of that is ion. We haven't really talked about ions all that much. So we're going to kind of introduce it today, and it'll be a bigger impact in Unit 3. So here's the thing. Here's ions. Here's the definition of ions. You already have this written in your vocab. It's atoms want to look like noble gases, meaning they want to have the S2P6. They want to have a full P shell, okay? They want to look like noble gases. So here's what they do. They're going to end up losing and gaining electrons to fill their highest energy level. So like, for example, bromine is argon 4s2, 3d10, 4p5. Now what argon's going to do, he's going to look around and he's going to try and add an electron, gain an electron to this right here so that he can be a 6, so he can look like a noble gas. So here's what you need to do, or here's what you need to know. Yeah, maybe. When an atom loses electrons, so when they get rid of their electrons, they form positively charged ions, and they always become smaller. If you're giving away your electrons, it's kind of like losing weight, you become smaller, okay? If you lose electrons, which are negatively charged, you're going to become positive because you're losing the negative and you have more positives. So in group 1A, those guys are going to lose 1 electron. In group 2A, they're going to lose their 2 electrons. And in group 3A, they're going to lose their 3 electrons. Okay, so that results in a positive charge. So I would write these above the group numbers on your periodic table. So above group 1A, I would write a 1 plus. Above group 2A, I would write a 2 plus. Above group 3A, I would write a 3 plus. Okay, now here's the weird thing. The D block, the ones that I color-coded yellow, the transition metals, they like to kind of do their own thing. So their amounts that they lose are going to vary. So we're not going to assign any numbers to them. All right. When an atom gains electrons, they form negatively charged ions and they become larger. It's kind of like gaining weight. You gain weight and you become a little bit larger. You're also gaining negative, so you're going to become negative. So group 5A, they're going to gain 3, and then they're actually going to take on a 3 negative charge, okay? Group 6A is going to gain 2 and have a 2 negative charge. Group 7A is going to gain 1 and have a 1 negative charge. Again, if you wanted to write this, like above 5A, if you wanted to write 3 negative, that's okay. If you above 6A, if you want to write 2 negative, you can. In group 7A, you can write the 1 minus. Okay, so losing electrons, you get smaller. Gaining electrons, you get bigger. All right, so now here's the trend. So ionic size, ionic radius, whatever, it's the same as the previous trend. You increase as you go from top to bottom in a group, but you get smaller as you go from left to right across a period for the same reasons as the previous trend, okay? The nucleus is pulling those electrons in closer to it. So on your picture here, there's a spot for positive ions and a spot for negative ions, but pretty much if you're going from left to right across the period, you're decreasing your size. And then generally increasing as you move down, okay? All right, so then we have this thing called ionization energy. What's the trend? You already have the definition in your vocabulary, but here's what it is. It's the energy required to remove an electron. So sodium right here has its valence electron right here. It takes energy for him to get rid of it, okay? Magnesium takes energy for them to get rid of their electrons, okay? So it's just not willy-nilly, it takes energy. So here's the trend, maybe if I can get to it. Here we go. So as you move down a group, the energy decreases, meaning it gets easier to get rid of those electrons. The atomic size is getting big, there's less energy required to move, so the farther you are from the nucleus, the easier it is to take your electrons, okay? As you move left to right across the period, it actually increases energy. It gets harder to take the electrons as you move across the period. The nucleus is pulling the electrons closer to it. So again, if you think about that nucleus with the electrons, he is pulling in those electrons so close and tight, it takes a lot of energy to lose them. On your notes, you're going to want to fill in generally increases and then generally decreases. Again, generally just means not all atoms like to follow these cool rules. Okay. And then the last one is my favorite, electronegativity. I don't have it written here, but the electronegativity, according to your notes, is the ability of an atom to attract electrons. So it's how attractive you are, okay? As you move down a group, you become less attractive to those electrons. As you move from left to right across a period, you actually become more attractive. Okay? So metals tend to be less attractive. Non-metals tend to be more attractive. All right, you have this picture. You just need to label the arrows. So you get more attractive as you move from left to right, and you get less attractive as you move down. But if you take a look, we have numbers that go with attractiveness. So the most attractive element on the periodic table is fluorine. He almost has a GPA of 4.0, and that's pretty attractive. The least attractive element, the ugliest element on the periodic table, is francium. He's got the GPA of a 0.70, so not attractive, not attractive. All right, notice group 8A. They don't have any numbers. We have to think about why. Since all elements want to look like noble gases, why do noble gases need to attract electrons? The answer is they don't. So it says, why doesn't group 8A have electronegativity values? Their highest energy level is already filled. Remember that was P to the 6th? So they are stable. They don't need to attract electrons from anyone. They already have the perfect amount. And our perfect amount, oh, never mind. Just kidding. All right, so in group 8A, they're already stable. They're already happy. They have a filled outer level. They have S to the 2, P to the 6. So they are good. All right, I hope you enjoyed. And if you have any questions, please reach out.